Assalamu alaikum. I hope you've been doing great, okay? Last time I gave you homework, if you remember, so let's say if you did your homework. What was the answer that you chose? In question 32, it says two spheres look identical and have the same mass. Don't forget. So we have two spheres and they look identical and they have the same mass, okay? But one of them is hollow and the other is solid. Which method would determine which is which? So we have two objects or two balls. They have the same mass, okay? But one of them is hollow. That means the inside of the ball is empty and the other one is solid, yeah? In this case, which method would determine which one is which? So, do we need to roll them down in an incline? That's one of the options. What would happen if you roll them down in an incline? So remember this, if they have the same mass, and of course the shape is identical, can we say the shape is identical? Sort of, because it says what? Two spheres look identical, so almost, yeah? And then, so in this case, we will not be able to see which one is which, yeah? But of course, there are ways where we can tell apart. All right, so roll them down in an incline, that is an option. I'll explain this in a second more. Drop them from the same height. What will happen if we drop them from the same height? Dropping them from the same height, that means no rolling, yeah? And we said if there's no rolling, that means the translational speed at the bottom will always equal to 2 times gravitational acceleration times the height, yeah? In this case, because we are letting them go from the same height, so they will have the same translational speed at the bottom. Weight them on the scale, that is also useless, that is because they have the same mass, yeah? Having the same mass would lead to the same weight as well. All right, so what about the first option here? So of course the correct option is A, but why A? Do you remember we said the distribution of the mass would affect the moment of inertia, yeah? In this case, if one of them is solid, their moment of inertia in this case is going to be what? 2/5 mass times the radius. What if one of them, let's say, is hollow? That would be like a thin spherical shell, right? But because they have the same mass, we cannot tell apart. But in terms of moment of inertia for a thin spherical shell, that is going to be 2/3 mass times these are radius squared, don't forget. So of course, once we roll them down, what will happen? This one, all right, will have, let's say, or if we're going to use this one here, let's say if we're going to use our equation here, for this one here, of course, the translational speed for the solid ball will be 10/7, and of course, times gravity times the height, okay? That is one of the things. What about for the hollow one? Of course, it's going to be V equals to, or V final, we can say, at the bottom is going to be what? 2 times 3, that is 6/5 times, let's say, gravitational acceleration, times gravitational acceleration times the height. So you would see that because they have the same height, or we roll them down at the same height, translational speed for the solid ball would be higher. In another way, the solid ball will reach the bottom of the incline faster than the hollow, let's say, sphere or hollow ball here, which in this case, it would be a very effective method to tell which one is which, yeah? The one that comes or reaches the bottom of the incline first would be the solid ball in here. All right. I hope it was... all right, so now question 37. In all the previous questions, of course, we had objects moving from the top or rolling from the top of the incline to the bottom of the incline, and we found the translational speed or the rotational speed for the object. Okay, but here it is almost like quite the opposite. The object is rolling down from the bottom of the incline to the top of the incline. All right, so what do we have in here? There is a coin, all right, that moves from the bottom of the incline, trying to reach the top of the incline. So it says what? A 0.02 meter diameter coin rolls up a 15-degree inclined plane. The coin starts with an initial angular speed. So the angular, here we have, remember, we have the angular speed, all right, which is 45.2 radian per second. Rolls in a straight line without slipping. Again, so that means it is rolling. How much vertical distance does it gain before it stops rolling? So we want the vertical height, okay? And of course, we're going to use the same equation that we've used, but of course, there is something else I want you to know. So pay attention here. One thing that you need to know that here we have the diameter. So, and of course, we have a coin. So you need to know the moment of inertia of a coin. The coin is like a disc in here, yeah? All right, so let's solve this one and say, by the way, we're going to use the same rule or the same type of equation that we used for the previous one. V, all right, the square root of the, let's say, a fraction multiplied by g times the height. All right, so here's the incline, right? And of course, here's the coin. This coin is trying to roll up, all right, without slipping. So of course it is rolling. And then this height is unknown. We're trying to find this height. And of course, this is 15 degrees, yeah? All right, it starts with an angular speed of 45.0 radian per second. Now, in order to answer this, first of all, we're going to write the equation for moment of inertia for a coin. Moment of inertia of a coin, it is, you know it already, yeah? It is 1/2 mass times the radius squared. All right, very good. So the equation that we need to find is, of course, V is equal to what? V is equal to the square root of a fraction here. We said 2 times denominator. That is 2 times 2 is going to be 4. Numerator plus denominator, that is 3. Multiplied by g, multiplied by the height here. This height is what we're trying to find. But before we do this, that is, of course, initial translational speed. Okay. Do we have the translational speed? No, but we have angular speed, yes? Of course, we can find this easily. So how do we do this? We know that the translational speed equals to what? Equals to angular speed multiplied by the radius. But do we have the radius? No, we have diameter, yeah? Okay, so what is the, we know that radius equal to, let me draw this one here. Radius equal to the diameter divided by 2. So in this case, we have 0.0200 divided by 2. We will get 0.0100, that is meter. All right, so this is the radius now. All right. Now, using the radius and angular speed, we can find the translational speed. So we'll say 45 multiplied by 0.01. Of course, we will get 0.45 meter per second, because this is translational speed. All right, so 0.45 meter per second. Now we have the translational speed, and of course this is initial. We can plug in the numbers into the equation. So let's see what happens next. So we have 0.45 equals to the square root of 4/3 multiplied by gravitational acceleration 9.81 multiplied by the height, which is in this case unknown, yeah? We're trying to find this. So how do you find this? Square both sides. All right, once you square both sides, of course, this 2 will cancel out. So what is the square root of 0.45? All right, let's get a calculator. The square root of 0.45, this is going to be 0.45 squared. The answer is going to be 0.2025, we can say. 0.2025 equals to 4/3. What is 4/3, by the way? Let me find the result of this. 4/3, 4 divided by 3, multiplied by 9.81. And the answer to this, of course, is going to be 13.08 multiplied by the height. So, of course, divide both sides by 13.08. So the height will become 0.2025 divided by 13.08, yeah? And of course, you divide the two. 0.2025 divided by 13.08. the answer will be 0.015, yeah? So 0.015, because this is the height, of course it is going to be in meter, all right? The digit after 5 is 4, so we're not going to round it up in this case. We'll leave it as it is. So this is the height that the coin will reach right before it stops. Stops from moving upward, of course. And this is how it is done. So let's summarize this real quick. What have we done first? You need to know the equation for the moment of inertia for the coin. Then we need the equation to calculate the height. And then, but we don't have translational. Instead, we have angular. So we convert angular speed to translational. But don't forget, we don't have radius. We have diameter. So you'll take half of it. Then you will find the translational speed. You plug it into the equation, square both sides, and then you will find the height. All right, and that was for this one as well. All right. Let's see what comes next. All right. Now, orbital satellites and black holes in here. And of course, we're not going to cover this, but there's one thing I want you to know, and that is, of course, the escape speed. Yeah. Remember, if you want to find the velocity, or we call it escape speed, we have an equation to find that. Of course, that is 2 times the mass of the planet, and then multiply by the universal gravitational constant divided by the radius of the planet. What is escape speed in general? Take a look. For example, we have a cannonball. Yeah. If you fire this cannonball with a certain speed, of course, after some time, gravity will pull it down. Or we can say this object's speed would analyze to 2 components. Yeah. Let's say here's the cannonball. Once it falls down, of course, there is a horizontal, let's say, component, and of course there is, let's say, the vertical component. So for vertical component, this one, gravity would affect the vertical component and pulls you down. And then as for the horizontal component, gravity has no effect on it. The horizontal component is constant, the vertical component is not, because gravity will be pulling it down, plus there's air resistance and all that. So, but the point is this. What happens if we fire the cannonball with a certain speed? After some time, it falls to the ground, yeah? What happens if we increase the speed? Of course, it will cover a larger distance, but then eventually it will fall down. What if the speed is enough, for example, so that, let's say, the speed of rotation here is going to be big enough, right? Gravity tries to pull it down, but then, of course, because it has a large speed, then the object starts circling or orbiting around the planet without falling towards the surface of the planet, or without falling, let's say, to the surface. But if the speed is greater than the speed of, let's say, orbital speed, then of course this cannonball or the object would leave the gravitational speed. And that is, once again, if the speed is greater than the escape speed, then the object would leave the gravitational field of the Earth, and of course it will go into space, and that is exactly what is called escape speed. The speed that is required in order to escape the gravitational field of that planet, whether it is on the Earth or any other planet. All right? That is what is called escape speed. As you can see here, escape speed depends on, it doesn't depend on the mass of the object, right? It depends on the mass of the planet, the gravitational universal constant, and of course the radius of the planet. All right, and these are cancelled, so we're not going to study them. We have question 48. Take a look. In this question, this is very important. It says a solid sphere rolls along a horizontal surface at a constant linear speed without slipping. Show that the rotational kinetic energy about the center of the sphere is 2/7 of its total kinetic energy. And you already know that 2/7, that is a fraction, which means 2 divided by 7, yeah? 2/7, 2 of the 7, yeah? Okay, so how are we going to do this? All right, let's do this. So we have a solid sphere. Let's get this one. What do we have? We have a solid sphere, yeah? So what is the moment of inertia of a solid sphere? Let's move this one a little bit down. Okay, here. So what is the question? by the way, we have a solid sphere, so the moment of inertia of a solid sphere, it is 2 over 5 mass times the radius squared. You do know this. Now the question is, it moves at a constant linear speed without slipping. Show that the rotational kinetic energy about the center is 2/7 if it is total kinetic energy. So we have rotational energy, right? Kinetic energy, of course. Let's use a fraction here. I need to erase this one as well. So it says, show that the rotational kinetic energy, so kinetic energy of rotation, all right, is 2/7 of the total kinetic energy, yeah? So kinetic energy total. And it says 2/7, yeah? So we need to show that the rotational kinetic energy is about 2/7 of the total. All right, so let's do this one together. Let's change the color. So first of all, we're going to write the rotational kinetic energy for what? For a solid sphere. What is the rotational kinetic energy? We know that the rotational kinetic energy is 1 over 2, right, of mass times speed, yeah? But because it is rotation instead of mass, we have moment of inertia, right, and then multiplied by the angular speed, correct? We can just write I times omega, and by the way, squared. But I'll write these cross so you know what happened here. All right, so and then what about for the total kinetic energy? For the total, of course, we have rotational kinetic energy and translational as well, yeah? All right, so in this case, we'll go with translational first, 1 over 2 mass times speed squared plus 1 over 2 again, moment of inertia multiplied by angular speed squared. Now, extending this, all right, so 1 over 2, what is the moment of inertia for a solid sphere? Once again, for solid sphere, it is 2 over 5, not 15, right? This is 5, and then multiplied by, once again, mass times the radius squared, yeah? And then multiplied by what? By omega squared. What is omega squared, by the way? We can just say, if I use r small here, so it will be best so I can cancel them out. Okay, so this is r squared, and then omega squared. What is omega equal to? We know that it is equal to translational speed divided by the radius all squared, yeah? Why? Because omega is squared, so squared and squared. Now that is for the rotational. What about for the total? Once again, we'll say 1 over 2 mass times velocity or speed squared, that is 1, plus, and then what else do we have? Again, for the rotational, it will be the same as the top part here. So 1 over 2, right, multiplied by the way, we can say moment of inertia for the solid ball was 2 over 5 mass times the radius squared multiplied by the angular speed squared, which is speed squared divided by the radius squared. All right, now changing the color. All right, take a look here. Now this R and this 2 will cancel out. This and this will cancel out. So and we can multiply these factors, yeah? All right, and of course this 2 as well. So what is left now? We can say that is going to be 1 times 2, that is 2. 2 times 5, that is 10. 10. What is left, by the way? Mass times speed squared. Mass times speed squared. And then at the bottom or lower part of the fraction, we have 1 over 2 mass times speed squared plus 1 times 2, 2, and then that is going to be 2 over 10. What is left? Again, mass and speed squared. Mass and speed squared. Very good. Take a look here. I have mass, speed, and mass and speed. I can take them as a common factor. Let's change the color. So this will become, or we can say it is equal to, right? What is it equal to? Let me write the upper part same, 2 over 10, m speed squared. And by the way, here I have 1 over 2 plus 2 over 10. If I take the mass and the speed squared as a common factor here. Now you can see I can cancel out these, yeah? I can cancel out this 2 and this 2, yeah? So find common denominator, and of course find the answer to this. So let's keep this the same, 2 over 10. Let me use color so you can differentiate between the two. All right, and let's use blue. All right, so in this case, what do we have? We have 2 over 10. And by the way, find common denominator, that is going to be 5. In this case, 1 times 5, that is 5 plus 2, that is going to be 7 over 10. All right, 7 over 10. Now you have 2 fractions being divided. So what will happen to this? We can say 2 times, or 2 over 10 times. We'll take this to the top, so we'll take the reciprocal. We'll kind of like do the upside down for the fraction. So in this case, it becomes 10 over 7. So the 10 and 10 cancel out. So what are we left with? 2 over, not 10, 2 over 7, yeah? 2 over 7. And this is the correct answer here. So we can say that the rotational kinetic energy, so we can say rotational kinetic energy, if I write it this way, oops, sorry, and kinetic energy of rotation, all right, over the total kinetic energy will equal to what? Equal to 2 over 7, and that is the proof, all right? I hope you got this. Now, study tip, a fast way to find the ratio between rotational kinetic energy to the total kinetic energy, or the translational kinetic energy to the total. Remember this, if you try to highlight this tip, and if you know this tip, of course, it will help you, of course, and saves you great time, by the way. What am I looking for? I'm looking for this rectangle here. So let's move this down maybe. All right. Let's do this. Perhaps I'll take it to a new page. So remember this, if you want to find the ratio of, let's clear this. All right. If we want to find the ratio of rotational kinetic energy of rotation to the total. To the total what? To the total kinetic energy. Let's go back to this. Kinetic energy of total. All right, here's what you need to do, yeah? Here's what you need to do. First of all, right, like we said, numerator, try to remember this, yeah? Of course, you need to know the moment of inertia for the object, yes? Moment of what? Moment of inertia of the object. And then after this, you'll use, let's say, numerator, right? And then divided by numerator plus denominator. Let me write numerator as well. Plus denominator. All right, I think I should use shortcuts in order to save some space. All right, so let's clear all this then. All right, so to find this, rotational kinetic energy over the total kinetic energy, right, here's what you need to know. Numerator, that would be at the top of the fraction, would be divided by numerator plus denominator, right? That is for rotational over the total. If you want to find translational kinetic energy, the ratio, by the way, divided by the total kinetic energy, in this case, we'll do the opposite. In this case, it will be denominator, all right? A denominator divided by numerator plus denominator. All right, let me show you a few examples here. All right. For example, let's say we want to find the ratio for what? For an object, let's say, that is 2 over 5, that is for a solid sphere, yeah? The numerator is going to be 2, right, using this equation. And then the bottom of this is going to be numerator plus denominator. So 2 plus 5 is going to be 7. That is for what? If we want to find the ratio of rotational to total kinetic energy. What if we want to find the ratio of translational kinetic energy to the total kinetic energy? Then of course we'll say denominator, right, as like this, divided by numerator plus denominator, which in this case here, of course we have 5 over 2 plus 5. By the way, denominator is what is 5, so just 5 over. And then the bottom will be numerator plus denominator. So 2 plus 5, that is going to be 7, and that's how it is done. All right, we have, and this is true, by the way, for all the other shapes. Let's take a look at these, yeah? Remember, for a ring, for example, yeah? And then what is the rotational kinetic energy over the total kinetic energy? We said the equation for the rotational, it was numerator, right, divided by numerator plus denominator. What is the numerator here? It is 1. So we'll say 1 divided by. And then the bottom, it was numerator plus denominator, yeah? So let me rewrite this one for you here. For rotational, let's write it here. For rotational, it was numerator plus denominator. For translational, it was the opposite. It was denominator over numerator plus denominator. So take a look here. For rotational to the total, numerator is 1, right? And then divided by numerator plus denominator. So 1 over 2, 1 plus 1, that is going to be 2, yeah? What about for translational? We'll do the opposite. You can see denominator is 1, so 1 over. And then numerator plus denominator, that is 1 plus 1, 2. Now, it is more obvious with other shapes, yeah? For example, disc or solid cylinder, yeah? In this case, this is moment of inertia for a disc. We'll say numerator is 2, yeah? And then divided by numerator plus denominator. So 1 plus 2, it becomes 3. So 1 over 3. What about the translational to total? It's going to be denominator over numerator plus denominator. So what is the denominator for this? That is 2. So 2 divided by. And then numerator plus denominator, that is 1 plus 2, it becomes 3 here. One more thing, solid sphere, for example. Here's the moment of inertia for a solid sphere, of course. For rotational to total, of course, we said numerator. What is numerator? 2, right? So here's 2. Divided by the total, numerator plus denominator, that is 2 plus 5, and here's your 7, yeah? All right, what about for translational to total? The translational denominator over this. So denominator is 5, so here's your 5, divided by what? And then I think let's keep it as clean as possible because we don't want any distraction here so that you can focus on this. So here's 5, right? So here's your 5 because it says denominator, correct? That is what it is. Plus numerator plus denominator, that'll be at the bottom. So 2 plus 5, and here's your 7. So it is true with all the shapes. And if you know the trick or how it is done, then you don't have to memorize any of these. Just remember the rule. Remember the rule. For rotation over a total, right, it is numerator plus this. If it is translational to total, it is denominator plus this. And that's all you need to know. All right. Moving on, there's a question here. This question is, right, I think it's question 7. Yes, I think it is 7. I think it was 7. You can double check with this. All right, it says what? It is more difficult to do a sit-up with your hands held behind your head than doing a sit-up with your arms attached out of in front of you. Explain. Of course, let's say here's a person, right? You're trying to do sit-ups, let's say. Maybe we could do something like this, and let's say this is your legs, right? These are not a very good one, but still, I believe you understand what it is, right? So if let's say you're extending your arms behind your leg, of course, it will be very difficult to do the sit-ups, yeah? But if your arm here, let's see if we can do the same thing again, yeah? This is you again, but this time your arms are here. It would be easier if you do this, it's a better picture. drawing here. So if your arms over, let's say, your chest or close to the center of your body, it would be easier for you to do the sit-ups. So why is this? Explain your answer. Of course, this is this has something to do with the moment of inertia. You remember we said the further the mass from the axis of rotation, the more the torque needed, and that is exactly what we have. If your arms are extended behind your head, of course, now the mass is like far from the axis of rotation. So in order for you to able to move to rotate your body about the axis of rotation, you need, or you, it requires a lot of torque, yeah? And that is the case. But once your arms are close here, so the masses are closer to the axis of rotation, less torque would be needed. So the answer to this would be performing a setup with your hands held behind your head is more difficult. Why? Because the mass of your arms is distributed far from the axis of rotation, which is your hip in this case, resulting in a greater moment of inertia. And a greater moment of inertia requires a bigger torque to rotate your body. All right. Now, so we're basically done with these questions, all right? Now we're at chapter 2, which is basically standard. We perhaps, all right, I believe it would be best if we save these questions for the next session, yeah? Just make sure you'll be reviewing what we have covered and keep practicing, because practice is what makes perfect. So remember this. I would prefer you go through the standard test and you solve the questions before I already solved them, and then you can compare your answers with mine to see how well you've done, right? So don't forget, that'll be, we are at chapter 2, standardized test preparation, you can say. So till then, keep practicing and stay safe. Assalamu alaikum wa rahmatullah.